Dear students, now let's start chapter 2, standard 12, electrostatic potential and capacitance. Now, first topic, work done on moving charge in electric field. Now actually this particular topic is not given to you in the text in detail, but this one is very important thing. So let's discuss it first. Okay, work done on moving charge in the given electric field. See, suppose here we consider a source charge capital Q which is at the origin of Cartesian coordinate system, and now in the space its electric field is prevailing. Now a small q charge is placed at point A in the Cartesian coordinate system, and now suppose we want to move that particular charge q from A to point B, and in this particular process we will calculate the total work done. Okay, now see here, first we consider the path A to C and then C to B. Now Q to A, this position vector is R1, so the distance Q to A or O to A, that is R1. Okay, so here on the curved path having radius equal to R1, charge small q is moved from A to C. Okay, so first we will calculate the work done on moving charge small q from A to C. So that is q integration A to C E dot dr, because after all E, that is nothing but the force acting on unit positive charge. So in the electric field E, force on charge q, that is q into E, and dr, that is displacement, force into displacement, that is work done. Okay, now here this work done will be 0. Why? Because electric field that is radially outward. So at each and every point on the AC path, the infinitesimal small displacement dr and electric field E both will be perpendicular to each other, and therefore the dot product E dot dr, that will come to 0. So work done to move charge small q from A to C, that is equal to 0. Now move it from C to B. So we can write work done from C to B, q integration C to B E dot dr. O to C, that is R1, and O to B, that is R2. So we can write the limits here, R1 and R2. So this is equal to q R1 R2, and at distance R the electric field, that is kq upon R square into R caret dot dr, the displacement, that is in the direction of the field. So we can write dr R caret dot R caret, that is 1. And here small q, k and capital Q are constants. So we can take the integration of 1 upon R square. Integration of 1 upon R square, that is minus 1 upon R. Take the limits R1, R2, then substitute the limits. First upper limit, then minus lower limit. So this is equal to kqq 1 upon R1 minus 1 upon R2. Because when we take first upper limit, so minus 1 upon R2, then minus 1 upon R1. So here it is written first. So now total work done on moving charge q from A to C, C to B, that is 0 A to C, then C to B, KQQ into 1 upon R1 minus 1 upon R2. So total work done on the path A to C to B, that is KQQ 1 upon R1 minus 1 upon R2. Now let's discuss another path. Suppose charge Q is moved from A to D and D to B. So work done on moving charge Q on path A, D, B. So first we will calculate A to D. So A, that is at a distance R1, D, that is at distance R2. So as previously calculated from C to B, like that we can write KQQ into 1 upon R1 minus 1 upon R2. And similarly D to B on the curved path, work done, that is 0. So again total work done on the path ADB, that is KQQ into 1 upon R1 minus 1 upon R2, that is from A to B, A to D, and then from D to B it is 0. So again we can see the work done on the path A to D to B, that is KQQ into 1 upon R1 minus 1 upon R2. It implies that on both the path the work done, that is the same one. So here the work done that does not depends on the path. It implies that we can say this thing, the electric field, that is the conservative field, or electric force, that is conservative force. Here work done depends only on the initial and final position. The same type of things that we studied in standard 11 in the chapter of gravitation. Gravitational field and gravitational force are also conservative field and force respectively. Clear to all of you?